They're coming in now.
Okay. Alrighty. Okay, there's something I gotta do here with the, let's see, PowerPoint. Remind me, let's see. Trying to remember how I get the cursor to change. I haven't done this in a little while. Center view. No, where is the, somebody help me here, Macintosh PowerPoint. How do I change the cursor for the mouse?
Do you mean to like a laser pointer or something?
Yeah. Or do I have to go to full screen to do that? We have to go to full screen to do that.
I haven't used PowerPoint in a while. Maybe one of the PowerPoint people.
Yeah, there it is. Yeah, I did have to go to full screen. So then we just make, oh, how about a green laser pointer? Okay, no, it's not doing it though. Oh, pen color, no. Oh, there we go. No, that's a pen. I don't want that. Maybe I just do this. There we go. Okay, that works. Good. Okay, thanks everybody. So should I just start?
Actually, I'll just introduce you a bit at the beginning, and then I'll just let you start. Does that work?
Yep.
Okay, so let's see, everybody's in. Yes. So
there's one that's waiting to come in. There you go. Okay.
Yeah, I think they'll be coming while we're starting. So we're excited to host the first talk of this new year on data-driven modeling in engineering and science. Our guest today is a special grade professor at the University of California, UCLA. And so Andrea Bertozzi is an applied mathematician recognized for her work in nonlinear partial differential equations and in graphical models for data science. She has expertise in fluid interfaces, swarming models, and crime modeling. She graduated from Princeton University with an AB, MA, and the PhD degrees in mathematics. Bertozzi has been at UCLA since 2003 and currently holds the position of Distinguished Professor of Mathematics and Mechanical and Aerospace Engineering and the Betsy Wood Knapp Chair for Innovation and Creativity. She is a fellow of the American Physical Society, American Mathematical Society, and Society for Industrial and Applied Mathematics. She has served as director of the Applied Mathematics program at UCLA since 2005. She is a Simons Math plus X investigator since 2017 and is a fellow of the American Academy of Arts and Sciences since 2010. In 2018, she was elected to the US National Academy of Sciences. Bertozzi is well known for finding unusual connections between disparate areas of science through mathematics as a common language. For those interested, she's recently published papers related to the ongoing pandemic, specifically on the difficulties of forecasting the spread of COVID-19. Today, she will be talking about total variation minimization on graphs for supervised and unsupervised machine learning. We'll have 5 minutes or 10 minutes for questions at the end. And during the talk, if you want, you can post questions on the chat box and we can maybe ask questions during the talk if you like, Andrea. So with this, the floor is yours. Thanks.
Thanks. Yeah, since I'm in full screen mode, if there are questions in the chat box, please interrupt me. That would be great. Thank you so much. So it's a pleasure to be giving the seminar. I'm sorry I can't show up in person. It would be really fun to visit Seattle any time of year, actually. You know, it's we get too much sun here in LA, so even if it's raining there, it's all good with me. So yeah, it's a pleasure to be here. So thanks. So I'm going to talk today about total variation on graphs and semi-supervised and unsupervised machine learning. So this is a good example of how to take ideas that were first developed for the physical sciences, right, and use them to develop algorithms for a completely different area. And so, let's see, there we go. Oops, So I'm trying to figure out now how to scroll through my slides with this cursor. Okay, there we go. I think I just used the arrows. Great. All right, so this is work that has involved quite a lot of young people. These are just a few names who have gone on to careers in lots of different places, universities all over the world, industry. And the research is motivated by some older work in image processing. So I thought I would start with an example from image segmentation. So these are all problems right now in Euclidean space, but we'd like to take these ideas and port them to discrete structures in high dimensional space for machine learning applications. So we're going to start with a couple examples from image segmentation. These are problems in the plane, so it's two-dimensional Euclidean space. And we're interested in segmenting information that is given by an image. So for example, if we take this face, this is Pascal Getterer, who was one of our former PhD students. And we have a function f, and it's so the function f defines this grayscale image. And there are a couple of models that are very famous. Actually, it's really one model that has variance, and that's the Mumford-Shaw model, where so let me also mention that everything I'm going to talk about today, they're all methods that are variational methods. So that means that we have to design some kind of energy functional, and then we try to find minimizers. So calculus of variations is very important here. So for this particular energy functional, we see that there are three terms. The first term is fairly well understood. It's the L2 norm of the difference between our desired solution U, which is going to be a piecewise smooth representation of the image. So it's the difference between U and F and the L2 norm, the square of the L2 norm. So from a statistical perspective, that's a least squares, okay? So it's like a least squares fit to our data. And then the smoothness is captured by these two terms. So we also want to find, in addition to a piecewise smooth function, we want to find the boundary of the smooth regions, right? So gamma is going to be where you see the jump discontinuities. It's a curve in the plane. And so the second term is demanding that U itself have some smoothness away from this boundary gamma. And then the last term here is actually the geometric term. So that is the length of the boundary. And so we penalize that term to avoid having very complex kind of fractal-like structure for that boundary. We want the boundary itself to have some smoothness. So we penalize that by introducing this length term. So that is the Mumford-Shaw model. And a variant of Mumford-Shaw, or I should say a special case of Mumford-Shaw, is the Chan-Besse model, which is, so the segmentation of Pascal under Chan-Besse is shown here. That's a piecewise constant representation of the data. So instead of finding a piecewise smooth U, we just need to find two constants, C1 and C2, and again, the boundary between the two constant regions, okay? And again, we're doing a least squares fit. And so, yeah, so that is, so this model here, we can also, for those of you who are familiar with data science, and I think there's a lot of people here who are, if we're to look at the k-means functional, this is like taking k-means and adding a geometric term to it, okay? And you can see that you get piecewise constant regions. It's a very useful, easy to implement model for image segmentation, and it was first implemented by Tony Chan and Luminita Besse using a level set formulation. But as I'll show in a few slides, you can also do this with other kinds of methods. Okay, so all right, so that's old stuff, and so now what I'd like to do is I'd like to talk about what is total variation and how does that relate to the Mumford-Shaw or the Chan-Besse model. Okay, and specifically that length of the boundary penalization. So if we have some boundary of some region in the plane gamma, And we have a function u that's a characteristic function of the region enclosed by gamma, then we can measure the length of the boundary by looking at the total variation of the characteristic function. So that's the L1 norm of the gradient of u, and in a weak sense, that gives us, that actually allows us, that measurement in a weak sense allows us to measure the perimeter, and we call that the total variation. So that's just some notation. And so, so this L1 norm of the gradient, we can actually relate back to the L2 norm of the gradient through what's called the Ginzburg-Landau functional. So the Ginzburg-Landau functional is a functional that has a diffuse interface parameter, epsilon. And the first term is the L2 norm of the gradient. So that imparts some smoothness again. So let me just mention the total variation semi-norm, for those of you who are not familiar with that, allows for functions u to have jump discontinuities. Whereas as soon as you turn the L1 norm into L2, that will penalize against the jump discontinuities and impart some smoothness. So what the Ginzburg-Landau model does is it includes a second term. And the second term is a double well potential. So W has two local minima, and W is a function of U. So if you want U to be a characteristic function, let's say +1, -1, or 0 and 1, and so it just takes on two different constants, then the way you can approximate that is with a smooth approximation, is by taking this W to be a smooth function, but one that has minima at the values of u where you'd like to see this function u predominantly match up to, right? So you're going to be basically, when you minimize the Ginzburg-Landau energy, it's basically a sort of a fight between two terms. One term is trying to push u into one of the two wells, and the second term is trying to smooth you. So you have this kind of balance. And from a physical modeling perspective, we see that epsilon actually has units of length, because I have a derivative here squared, and an epsilon here, and a 1/epsilon here. So epsilon is naturally something that has units of length, and it results in minimizers of this energy that have sort of a small transition layer between the two energy minima of W. So one of the things that's well known from PDEs is that in the limit as epsilon goes to 0, we actually have gamma convergence of the Ginzburg-Landau functional to the total variation semi-norm. Okay, so that means that if you want a smooth approximation of total variation, one way to do that is using Ginzburg-Landau. Okay, so now what I'd like to do is look at the Ginzburg-Landau model, and I'd like to think about how do we find those energy minimizers. Well, the simplest thing you can do is gradient descent. And if you take the L2 gradient descent, or gradient descent under the L2 inner product, we end up with a famous equation called the Allen-Kahn equation. So the Allen-Kahn equation says that we're going to be evolving u according to this right-hand side, where the first term is the heat equation, and the second term is the first variation of the double well potential. And we see that that's just minus W prime of u, and that term alone is going to be literally pushing u down into one of the two wells. So this is famous model of material science. And in terms of the dynamics of the Allen-Kahn equation, in the small epsilon limit, what we recover is actually motion by mean curvature of the interface between the two values of u. So that's kind of cool. Now, in 1992, Merriman Benson-Osher noticed that if you want to do motion by mean curvature, and inspired by the Allen-Kahn equation, right? So you can think of the Allen-Kahn equation as basically having a slow time scale for the heat equation and a fast time scale for this descent into the double well potential. That fast descent actually can be done instantaneously if you want to. And moreover, we know a priori which well the solution will go to, because, if you just look at the double well potential, all you need to do is figure out for that ODE dynamical system, you just have to figure out which well you're closer to, and then go to it. And that can be done in a simple thresholding step. So the MBO scheme basically involves solving the heat equation, starting with a characteristic function. We solve the heat equation for a short time. Then we take the solution to that and we threshold it and we get a new characteristic function. And then you just iterate. So that's called the MBO scheme. So the MBO scheme basically allows us to approximate motion by mean curvature, which is a very nonlinear dynamic for a curve. We can approximate that by taking characteristic functions and solving a linear heat equation for a short time, followed by the threshold step. So it takes a nonlinear, it basically approximates a nonlinear dynamics on the curve by a combination of a linear PDE in the whole plane and thresholding. And so basically you get to take one curve and just evolve it to the next one and the next one by these steps. Okay, so that's the MBO scheme, and that's very important if you wanna use this idea of motion by mean curvature to solve some of these segmentation problems. So in fact, Salim Asadoglu and Richard Tsai did that. In 2006, they published a paper extending the piecewise constant Mumford-Shaw model for image segmentation. They took this MBO scheme for motion by mean curvature and showed that you could extend it to the what's essentially the Chian-Vessey model. You can minimize that with a method that looks very much like the MBO scheme, and it's very, very efficient. You don't have to do level sets. You can just do a combination of the heat equation and thresholding. It's not, so for image segmentation, of course, you need the image. So you're not just solving the heat equation, you're solving a penalized heat equation. And I'll get into that a little bit more. Okay, so we now have a body of tools from Euclidean space for segmenting images and for, doing diffuse interface approximations of sharp interfaces. And we'd like to take those ideas and we'd like to figure out how to use them efficiently to do clustering and segmentation of data in high dimensional spaces, but typically discrete data. So we're no longer going to be thinking about solving these problems in Euclidean space, but rather we're thinking about using graph structures. Okay, so we want to find a parallel between all of these ideas in Euclidean space that we're using for these classical image problems and transfer them to machine learning problems on graphs. So we've looked at this minimal surface problem or penalized minimal surface problems in Euclidean space, and those will turn into min-cut problems on graphs. The Laplace operator in Euclidean space will have an analog over here, and that's the graph Laplacian on the graph. So under the hood, when we try to solve the MBO scheme, one very useful method, since we're just looking at the heat equation, would be a pseudo-spectral method, which involves Fourier modes and the fast Fourier transform. And so the analog of that is going to be projecting onto eigensubspaces of the graph Laplacian in our machine learning problem. And the fast Fourier transform does not have an obvious analog, but we can look at various projection strategies and various approximation strategies for the graph Laplacian. And the two that my group likes are for a low rank approximation of the graph Laplacian, the Nystrom extension, and for sparse approximations of the graph Laplacian, a Rayleigh-Chebyshev algorithm. And one major difference, and I really should have put a different color here, which is between these kinds of methods and these kinds of methods, is that in the machine learning context, the graph Laplacian is created from data itself, right? It doesn't live independently of the data. And because it's created from the data, there's a lot of redundancy. And so because of that, we can often get very good results with only a small percentage of spectral modes. And so that's a big difference between solving PDE problems and trying to use these ideas in machine learning. Okay, so now what I'd like to do is I'd like to introduce weighted graphs for big data applications. So imagine that you have a bunch of vectors. So these could be very high dimensional. We often call them feature vectors. I have the US Congress here, which is sort of an ironic example given what happened just a few days ago in the Capitol. But one example that we worked with are voting records from the US Congress, in particular the House of Representatives, because they have more members than the Senate. They have 435 members, so that's a larger data set. It's still not terribly large, right? But it's a larger data set. I mean, there are lots of examples. Another example is hyperspectral data cubes. So hyperspectral cameras are cameras that take data in a very refined way in the electromagnetic spectrum. So instead of just measuring, say, like RGB pixels, it's going to be measuring lots of different wavelengths, like maybe 128 or even over 1,000 wavelengths, depends on the camera, right? And different cameras are measuring different parts of the EM spectrum. But these are very high dimensional data sets. So every pixel has many, maybe 100 or more dimensions. Okay, so you can take these high dimensional data sets and you can create a graph. And so when you create the graph, every single node on the graph is going to correspond to one of your pieces of data. And these are weighted graphs. So the weights basically measure how similar are the pieces of data. So this is one way to measure that. You can take some metric that measures the difference between two feature vectors and then put it in this exponential function. And so that's a lot to absorb, but basically the idea is that if you have two pieces of data that are very similar to each other, then they should have a strong weight. So the weight is close to 1. And if they're very dissimilar from each other, then you'll have a weight that's small, okay? And so we're trying to figure out what is a natural partition of this graph, of this weighted graph, right? That's basically kind of the idea. And so one of the problems that we're going to want to look at is a minimum cut. So the minimum cut means that we're taking our graph, and all these edges correspond to, they all have weights that measure the similarity of the data on the nodes. And we'd like to figure out how to partition the graph so that when we partition it, i.e. we color some nodes one color and the other nodes another color, that all of the weights, the sum of all the weights between unlike nodes is minimized. So one way of measuring that is through, again, a total variation functional, but now this is a functional defined on the nodes of the graph. So F is going to be a function that takes on values on the nodes, and these are the weights. And so we're trying to minimize the sum over all the weights of Fi minus Fj in absolute values. So that means that if your assignment function F has the same value, say these two nodes have the same value, then you don't count that weight. And so we see that if they have the same value, then the absolute value of the difference is 0. So we won't count that weight. But if they have different values, like these two, then the edge weight between them will be counted, right? So that's the idea, and that's what total variation is. And this is equivalent to the graph cut metric. So for people who have heard about the graph minimum cut problem, minimizing the total variation is exactly the same thing. It's just a different mathematical way of writing it. And by writing it this way, we can introduce variational calculus and look at it as an optimization problem in that setting. Okay, Okay, so now what I'd like to do, I'd like to take this idea of the total variation minimization on the graph, and I'd like to think about how we've done it already in Euclidean space, right? Euclidean space, we introduced TV, and we notice that there is this smooth approximation using the Ginzburg-Landau energy. So it turns out you can take that idea and you can extend it to graphs. Okay, so this is work that I did with Arjuna Flenner a little while ago, but when we did this work originally, it was a bit of a leap of faith because nobody had looked at Ginzburg-Landau on graphs, but we thought we'd give it a try, and we were quite impressed with how efficient it was to solve and also how well it performed. So let me give you kind of the nuts and bolts of how this works. So once you have a weighted graph that's constructed from a data set, what you can do is construct something called the graph Laplacian. This is a matrix operator. So our weights are going to be minus the weights are going to be the off-diagonal elements of the graph Laplacian. And the degrees of the nodes, which is the sum of all the weights going into each node, that corresponds to the diagonal of this graph Laplacian operator. So once we have our graph Laplacian operator, we can then define energies. And so a natural energy is the inner product of U with Laplacian of U. So U is going to be our assignment function on the nodes of the graph. So U is being evaluated on nodes, and the graph Laplacian describes connections between nodes. And so you can take that as a matrix operator and apply it to any function defined in the nodes. And then we can take the inner product of U with L of U, and that defines a lovely quadratic energy that is often called the Dirichlet energy. So here's our Dirichlet energy right here. And we see that it involves the weights, the weighted graph, and the assignment functions. Okay, and now for various types of data, there are different normalizations of the graph Laplacian. So there's a symmetric normalization where we normalize by the degrees of the nodes. That helps when you have outliers, which can arise certainly in image processing applications. And there's also a random walk Laplacian. But basically in my group, a lot of the methods that we use are based on symmetric Hermitian matrices. So we are typically using either LS here or the original graph Laplacian L. And so whichever one you choose, you can then write down a modified Ginzburg-Landau energy. So this one here is our semi-supervised machine learning energy. So how do we see that? Well, so first of all, this term here is the semi-supervision. So U is going to be taking on values on the nodes of the graph, and U naught is going to be our training data. So that means that we're given our data set. The data set now lives on a graph, and some of the nodes we know a priori from other sources, we know what the assignment should be. And so that is predefined, and that's our training data. And so that's defined here as U naught. And this term is going to be a sum over all of so lambda is going to be a characteristic function that defines the training data. And this term here is going to be telling us that we want to minimize a least squares fit to the training data. So it's a soft constraint on the training data. The rest of this is our Ginzburg-Landau energy. So this term here replaces the L2 norm of the gradient of U in the original Ginzburg-Landau model. That's our H, for people who are familiar with Sobolev spaces, that's the H1 semi-norm. And this is the double well potential, which I've written out for a particular choice of the double well. It's the quartic polynomial. And this double well is taking on, has minima at plus and minus 1, right? Okay, so that's the model. This was something that we just kind of wrote down, leap of faith at the time we did this work. And what's beautiful about this particular model is that the similarity graph from the data only enters into this minimization problem in this first term here. and it only involves the graph Laplacian. So if you have an efficient way of calculating properties of the graph Laplacian, which we do, there's a lot of, so we were borrowing a lot of ideas that were already out there for treating the graph Laplacian. So there's a lot of good methods for the graph Laplacian. So if you have methods, then you only need to worry about the graphical structure for this term here, because this is evaluated at pointwise on the nose of the graph, and so is this term here. So if we look at the first variation of this, if we're going to do a gradient descent energy, then we get sort of a graphical heat equation term here, and then we have ODE kind of behavior with these two terms here. And that can be solved very efficiently, if you have a way to treat the graph Laplacian. Okay. So this works very well. And so once we discovered it worked well, of course, one wants to prove something, right? So if we look at an energy like this, it turns out that the graphical version of the Ginzburg-Landau model, one can actually prove that has gamma convergence to the total variation semi-norm on graphs. So this is work with Yves van Gennep that we published about 9 years ago now, that proves this rigorously. So it meant that our leap of faith could be made rigorous, but notice that to prove this result, we had to modify the graphical Ginzburg-Landau model slightly, right? So there's no small parameter here. This is the Dirichlet energy right here. And then this is the double well potential. So we keep the 1/epsilon term in front of the double well, and we remove the epsilon from the Dirichlet energy. So, and that's because in the Dirichlet energy, the space that we're working in for the graph structure is a fixed finite set. We're not taking the limit as the number of nodes of the graph goes to infinity. No, it's a fixed number, and it's a discrete functional. And so there's no like small length scale here, which means that epsilon is only showing up on this term here. But nevertheless, using some classical ideas from functional analysis, you can prove gamma convergence to the total variation semi-norm, and that's the result we get right here. So that's nice. So it tells us that the Ginzburg-Landau energy ought to be a reasonable approximation for the graph cut energy. So basically, what this prior model then, if we don't take epsilon small here, then this model ought to be approximating a graph cut energy here, and then the semi-supervised learning with the least squares fit here. Okay, good. So now once you do that, it's very natural to think about how to do this quickly. And remember, I introduced the MBO scheme, and indeed that extends very naturally to graphs. So the MBO scheme was a scheme for minimizing total variation in Euclidean space, right? To do curve shortening in Euclidean space with motion by mean curvature. Well, we can do that for solving the graph cut minimization problem. Now, if we do this for semi-supervised learning, we have to introduce the learning part of the problem, and that shows up here. So it's just a simple penalty on the right-hand side of our graph heat equation. So this is the graph Laplacian. We have a minus sign here instead of a plus sign like we do in Euclidean space, and that's just a convention because in computer science, our graph Laplacian is typically a positive definite operator rather than negative definite. So that's just a convention, a sign convention, but it is the analog of the heat equation. And so we also have another term, a forcing term, which is for the semi-supervision, and we're going to alternate a step of this model with the thresholding step. And this is very, very fast. If you have a good way to approximate the graph Laplacian, which we do, then you can do this very, very efficiently, and it converges sometimes just in a few iterations. You get convergence. We were really impressed with how well it behaves. So here's kind of in a nutshell what the algorithm is like. So you create a graph from the data, but this is more or less step one is more of a theoretical step. So you have to choose a weight function and then create the similarity graph. But in practice, we don't actually need the whole graph. What we need are ways of approximating the graph Laplacian. So if we have eigenvectors and eigenvalues of this symmetric graph Laplacian, and we don't need all of them, we can often use a small subset of them, then we can project onto those to give us this term here, to basically be able to approximate the flow for this term. So that's step 2. Then we initialize our assignment function u, and then we iterate this 2-step scheme. So now under the hood for the graph Laplacian, we, as I said before, in my research group, there are 2 approaches that we find particularly useful. One is a sparse approximation. So you can use a k-nearest neighbors approximation for the similarity graph, and then use a Rayleigh-Chebyshev method for computing some of the eigenvalues and eigenfunctions. That's one option. The other option is the Nystrom extension. So the Nystrom extension is a different way of approximating the graph Laplacian. It's a low rank approximation rather than a sparse approximation. Okay, and so these ideas, so far I've explained this to you for the problem of binary segmentation with the double well potential. So the question is, in actual machine learning applications, you have more than just 2 classes typically that you want to find. You often have data sets where you can have 5, 10 or more classes. So how do we take these ideas and extend them to multi-class segmentation or clustering for big data sets? Okay, so there's a couple of ways you can do this. So of course, very naturally, if you have a binary method, you can do recursive binary partitioning, right? But that's not always the best thing, if especially, let's say like the natural data set is 3 classes or 5 classes. It's not a power of 2. We'd like to have a method that is much more general for multi-class, and ideally to tell us how many classes there are. So that's kind of where I'm going with this, from semi-supervised to unsupervised segmentation. But let's stay in the semi-supervised space for the moment, and let's think about the multi-class problem. So it's very easy actually to generalize the double well potential to a multi-well setting. And so we do that by looking at, instead of having like a double well potential on the line in one dimension, we augment the space to multiple dimensions, where the dimensions are the number of classes. And then we look at multi-well potentials like this one here, where the wells live at the corners of the simplex in k-dimensional space. So that's what we look for. So these SJs are the corners of the simplex. And you can write down multi-well potentials. People have asked me, why are you using the L1 norm here for your multi-well potential? And that's basically because we want to avoid having like a very, very flat minimum in the center of the space, a flat, like, not minimum, but a flat region in the center of the space where you can kind of get stuck. So that's why for for problems with many classes, that can be an issue. So the L1 norm here tends to be a bit better. But nevertheless, this bottom line is this is a multi-well potential. And the Dirichlet energy, one of the beautiful things about this model is the Dirichlet energy doesn't change. I mean, the U's become vectors in this k-dimensional space, but this inner product is the same. And in particular, the graph Laplacian is the same. So if you have a method for computing the graph Laplacian and computing, say, eigenvalues and eigenfunctions of that operator, you do that once, regardless of how many classes you have. So this is basically, this operator here is essentially independent of the number of classes. So it scales incredibly well in terms of this number k. And then finally, you have the semi-supervision as the least squares fit to the training data. So this extends incredibly easily to multiple classes, this model, and you can do semi-supervised learning, and it's very, very efficient. So here are some examples with a multi-class case. So this is image labeling. So we're given this image of cows. what we'd like to do is have a user go in and define regions of the image, which are marked by these sort of pen colors. And we'd like to find these same objects in a different image, right? So we label this image and we find the cows in another image. And this can be done very efficiently with very little training data. And this is, in case you're wondering what graph are we using here, this is actually a graph made up of feature vectors that involve the non-local means functional, which basically takes patch neighborhoods of the image. So we did this as an example of high dimensional feature vectors. That's easy to visualize. That was the point of using this example. So every pixel in the image has a neighborhood around it, and we take that whole neighborhood as the feature vector associated with that pixel. So it gives you a high dimensional, large data set with a lot of redundancy. So it's a good example for this kind of method. And then, so you can also take this idea and you can do the MBO scheme. So the way that works is you end up solving a heat equation on these vectorized assignment functions and then thresholding to the corners of the simplex. So if you have an efficient method to threshold to the corners of the simplex, which is not hard to do, then you can just alternate these steps, and you can write it all in terms of, the heat equation part can be done in terms of just some basic numerical linear algebra involving the eigendecomposition of the graph Laplacian. So I'm gonna, so here's some examples of results. This is with the MNIST data set. So given this crowd here, you probably all know this data set. MNIST is 70,000 handwritten digits. A lot of people use it for testing methods. And so the takeaway here is that we can solve this problem with semi-supervision with a very small amount of training data. With pretty high accuracy. Now there are some methods that are supervised, like the support vector machine result here, that has very, very high accuracy, but it assumes that most of the data is training data and only a small part of the data is unknown. Whereas here, we're using most of the data as unknown and just a little bit as training data. And I would argue that in real world settings, this is going to be much more of a common situation than one finds with, these special examples that you can pull off the internet to test your code. That in real life settings, you probably won't have a lot of, precise training data. So what this method is doing is it's using inherent structure of the data and natural boundaries in the data to figure out how to segment the information. Okay, so this is another piece of the puzzle. So instead of using a sparse approximation for the graph Laplacian, you can use the Nystrom extension, which is a low rank approximation. And so what this does is it takes the weight matrix, which is kind of written out here in block diagonal form or in block form. And it's a symmetric matrix. So this block is the same as this block here. And if you take the X component of your data set versus the Y component, if you take the X component to be small, and you only measure the pairwise interactions within the X set and between the X set and the Y set, and this is often done with random sampling, but you do not calculate this big block submatrix down here, you can approximate the big matrix W by this approximation here that doesn't involve the WYY calculation, which will allow you to do this, to approximate W with something that is closer to an order n calculation than order n squared, where n is the number of nodes of the graph. So that's one of the dangers with any graphical model for machine learning, is that in theory, you want to be measuring all the pairwise interactions between all the feature vectors, and that gives you an order n squared calculation. So the Nystrom extension is a way to do a low rank approximation without doing an order n squared calculation. Likewise, sparsifying the graph is another way to do that, right? With like a k nearest neighbor sparse approximation. Okay, so now in terms of real physical data, I know that that's one of the themes of this seminar. Here are some examples with hyperspectral video. So these are videos that are taken with a long wave infrared camera. And if we look at the eigenfunctions from the graph Laplacian, so this is calculated using a spectral angle approximation, the cosine angle, rather than the L2 norm for the similarity matrix to compute the weights. So that's what we do, and so once you have the graph Laplacian, you can use the Nystrom extension to calculate some of the eigenfunctions of the graph Laplacian. And when you look at them, you see that the data appears to be pretty noisy. So what are we looking? What is the actual scene? So since it's long wave infrared, I can't show you optical images because they weren't measuring them. But the eigenfunctions start to give away what's in the image. And so what this is actually an image of a gas plume release in the desert in Utah. And you can kind of see like a little bit of the mountains here. This is like the sky over the mountains. And then this kind of object here, that is part of the gas plume. And there's some foreground information here, but very, very noisy. And right, and this, who knows what this eigenfunction is doing. But what you can do is take these very noisy images and you can threshold them. You can threshold the eigenfunctions to try to tease out some training data for semi-supervised machine learning. So that's what my student Katie did. She thresholded the eigenfunctions and said, hey, why don't we find the plume here with a strong threshold? The green is part of the mountains, the blue pixels are part of the sky, and the brown pixels are the foreground. And she just took that as training data and then, used the MBO scheme on graphs to, to figure out what the rest of the image should look like. So she did a random initialization of all the other unknown pixels. And then after just a few iterations of MBO, this is what she gets. So this is the classification, and it's really quite clean. So you can see these are different video frames, and that orange stuff is the gas plume, and the blue is the sky, and the green is the mountain, and the brown is the foreground. And this is much, much cleaner than what we see in the original data set. And it's a result that, other people have worked on this data and we're really quite impressed with the result. You can also see that the gas plume is actually semi-transparent. And so in the center of the plume here, there's a lot more transparency, and you're picking up the information behind the plume, right? You can see the sky over here and the ground over here. And as the plume moves across the scene, those background pixels do not change, which is of course what you would expect to see. Okay, so that's very nice. Now back to the mathematics underlying these methods. It turns out that there's a really pretty connection between MBO, the MBO scheme, and the graph total variation. It's a different connection than what I talked about earlier, but it turns out that in Euclidean space, you can take the Mumford-Shaw model and you can look at this MBO version of it, and you can look at this particular diffuse operator here, which is from the heat equation step, right? Where you're just, so here L is the graph Laplacian, but in Euclidean space, it would be just the standard, differential operator, or the Laplace operator. So this is an evolution of the heat equation for a small time step tau. So it's an analog of this Euclidean space problem. And so, so first of all, this operator you can show is positive semi-definite. No surprise, it conserves mass. But then the important thing is that this quantity here, which which is sort of what the MBO step is doing if you kind of parse it. So what is this quantity? It's the inner product. So F is our, so by the way, I'm going back to the binary case here for the moment. So assume that our binary function is going to take on values of 0 and 1, then if I'm looking for a characteristic function, then 1 minus the characteristic function is the exterior of the set, right? So I'm taking the inner product here of 1 minus F with this diffused version of F. What that does is it gives us kind of the amount of area that you move with the MBO scheme. But it's going to be a thin strip around the boundary. And it turns out that quantity actually approximates the total variation semi-norm. So we know this has been proved for Euclidean space, and you can actually prove it for the graphical setting as well. So what does that do? It actually gives you so the MBO scheme at face value doesn't look like it doesn't look like a variational problem, but actually hidden in it is actually a variational problem. So you're actually minimizing this quantity. And so we can show that for graphs. And then we can also take the Mumford-Shaw model, which is an unsupervised model rather than semi-supervised. We can take the Mumford-Shaw model and we can also extend that directly to the graphical setting. So we did this for the plume data. This is work by my other former PhD student, Hui Hu. And it basically uses a scheme very similar to the semi-supervised case, only you don't have the semi-supervision, right? So you have instead the least squares fit to the centroids from your partition in the Mumford-Shaw model. Okay, so it's unsupervised, but it does have a fixed number of classes. So you can try this on the plume data for different numbers of classes. And you have to try a bunch of realizations of the minimization problem, because you don't always get the right number of classes. But when it does work, you get some rather nice unsupervised segmentations of your plume and your sky and your foreground and the mountain. Okay, so in case you're wondering how these methods compare with some classical machine learning problems that don't have the geometry built in, you can look at that. So for example, the original k-means model on the plume data set, what we see is it just chops the plume in half. It really doesn't give you what you would want for k-means. Now you can do much better with something called spectral clustering. So spectral clustering does use the graph Laplacian like we're using. It uses eigenfunctions for the graph Laplacian, but the difference stops there. So k-mean, what spectral clustering does is it takes some subset of eigenfunctions and then it runs k-means on the eigenfunctions of the graph Laplacian. So when you do that, you pick up some of the artifacts that we see in the spectral data, like this weird kind of partition of the sky. But you do get the plume, right? So here's the plume showing up very nicely with spectral clustering. Right, so, and this work is joint work with Hui Hu and also Justin Sunu. I need to give Justin some credit here because Justin did the calculations of the eigenfunctions of the graph Laplacian for this work and for the prior work that I showed with Katie Mercurio. So I'm looking at the time and I think I'm running low on time, right? So I wanted to skip through some of these slides and just mention some other problems that you can solve with these methods. And these are problems that are also unsupervised, very classical, machine learning problems like the Cheeger-Cut problem. So the Cheeger-Cut problem basically says, let's try to take our data and segment it by minimizing the graph cut divided by a penalty term involving the sizes of the two sets that you're trying to partition, right? So that the penalty term basically avoids lumping all of the data into one class. It forces you to make a two-class segmentation. And there are lots of variants of this kind of binary cut segmentation, like the ratio cut and the normalized cut, also the Cheeger cut. So people often try to solve these problems with linear approximations, right? Just using some eigenfunctions of the graph Laplacian. So the point here is that using this kind of nonlinear viewpoint, you can actually literally solve the nonlinear problem. You don't have to do kind of loose approximations. You can really solve the fully nonlinear problem using the variational calculus and using diffuse interface approximations or the MBO scheme. So that's work that we published a few years ago. And then I don't have a lot of time because we're getting close to 10 here, but I wanted to mention that in the last couple of years, we've made a lot of headways into a really hard graph cut clustering problem, and that is community detection on networks using something called modularity optimization. So this is a method and an idea that was developed in the network science community, popularized by Newman and Gervan in 2004. There's been thousands of papers in the network science community studying modularity optimization. It's a very NP-hard problem. And one of the reasons that it's so hard is that you're trying to segment networks or graphs where you don't know how many subsets you want to have, right? That's one of the tough parts is for something like spectral clustering, you specify the number of categories. But for modularity optimization, part of the optimization problem is to figure out how many there are. So it makes the problem much harder computationally. But it turns out that modularity optimization can be written in the form of a penalized graph cut problem. So once you do that, we have all the architecture that you need to try to design an optimization strategy based on that viewpoint. So that's what we've been doing. And one of the takeaways here, and I'll just kind of say big picture wise, modularity was invented to study partitioning of networks, communities and networks. But it can also be used to study natural partitions of similarity graphs in data science. And if we use the methods from network science, they tend to be computationally prohibitive for big data. But if we use our viewpoint, right, looking at this as a geometric problem in a high dimensional space, the algorithms can be quite efficient and can actually be used to do unsupervised segmentation. So cutting to the chase, right? So if I were to take, say, the MNIST data set, and I were to take, let's say I want to segment all 70,000 digits of MNIST with no training data at all. I don't know anything about it. It's just a data set. I can feed this data set to a well-known algorithm from modularity optimization, and it does very well, right? This is the Jen-Louvain method. It tells me that I actually have 11 digits, not 10. Okay, well, you might think that's wrong, but actually it's a correct answer because it takes the ones and it breaks them into two categories. So some of the ones have a flag and some of them are just like a stick. So it breaks them into two categories, but we consider that a correct classification. So it does this with a 97% accuracy, but it takes a very long time. Right. So the advantage to using one of these geometric methods like our MBO-based method is that we can solve this problem in a few minutes rather than taking this huge number of seconds to, rather than needing like almost 11,000 seconds to solve this problem, we can do it in orders of magnitude faster time, right? Which means that we're sort of opening the door to use modularity optimization for machine learning. So we've extended this idea. My student, Zach Boyd, who is now a postdoc in Chapel Hill, has found ways to really make this machine learning utility of modularity very efficient, looking at almost convex approximations or actually equivalent formulations of modularity. So that there's our plume data, and also with Mason Porter, we've taken some well-known stochastic block model methods like the planted partition model from Newman for networks, and also figured out how to optimize this problem, this optimization problem to solve both network science problems and machine learning problems. So that's a paper that just came out last year in the journal Nonlinear Science. So I think given the time, I should probably stop. And thank you all for listening to my talk.
Thank you, Andrea.
Yeah, sure.
So we're gonna open the floor for some questions, if anyone has questions. Maybe I'll start. Oh, okay, wait.
Yeah, I can't see the questions, so, or maybe I can chat. Yeah, there they are. Okay.
Yep.
Yeah. Okay, good. So PowerPoint. Yeah, we can make that available. Let's see. Yeah, in the MBO, the thresholding step assumes each point in the heat equation converges to the nearest energy well. This takes advantage of properties of the Dirichlet energy lead. Okay, so let's go slow here. Let's slow down. Put on the brakes on the question. So the heat equation is a separate step from the threshold step. So the threshold step pushes the solution to the nearest energy well. That's the second part of MBO. The heat equation is another step, right? So you're alternating those two steps. So I just want to make sure everyone understands that. So in the MBO, so it says in the MBO, the threshold step, this is from Zach Nicolau, the threshold step assumes each point in the heat equation. Well, this would be each point after the iteration of the heat equation, right? Converge. So it's not a converge. You literally modify it to take on the value of the nearest energy well. And so the Dirichlet energy, you should think about minimizing the Dirichlet energy, which is your heat equation step. And you're not minimizing it on that step, you're just flowing in that direction. So that's an important point here, is that if you look at the original Ginzburg-Landau model, the heat equation step is on a slow time scale, and the threshold step is on a fast time scale. Or sorry, the energy well descent is a fast time scale. So what MBO does is it takes the fast time scale and just goes to the T infinity limit immediately. Okay, but the heat equation step is still happening on the slow time scale. So that's important to understand. And with MBO, as is well known, I think, generally speaking, for diffuse interface methods in general, but MBO in particular, you have to be very careful as to what your time step is. I mean, you have a range of time steps that you can take for which it'll work, but if you take too big or too small a time step, you're going to end up with different results, right? You'll get some kind of pinning, typically. And it's because you don't have the right balance between the time scales of the two terms. So it's a little, you have to be careful, right? You can't just blindly do these steps and assume they're going to work. You have to be careful about your time step in that problem. Okay, Zach, you're welcome. Yeah, it's a really good question, and it's a question that gets into the nuts and bolts, and I really appreciate it when somebody asks a question like that. So yeah, so I will say that, you know, there are parameters here, and you do have to be a little bit careful, but you know, there are pretty wide ranges where you get fairly robust results. The same thing is true in terms of the parameters in these models. The construction of the similarity graph has a parameter as well, right? And that's a parameter that kind of is more of like a parameter for length scales on the graph. And that's also an important one too, but it's one where, again, you have, you know, the method is somewhat forgiving, but if you go way outside of the bounds of sort of the range of parameters you should be taking, then you probably will get some strange results. But that's also well known for similarity graphs.
So I have a sort of follow-up question in terms of intuitively, how can we think of the diffusion term when the MBO scheme or when we're doing this image segmentation? What is this? Usually diffusion is associated with some kind of smoothing, but in this case, I guess the thresholding does the sharpening.
It's you can think of it as smoothing of the labels of the assignment, right? So so if in the image segmentation problem, what like if we go all the way back to Pascal, let's see, I gotta get on the slides here. If we go all the way back to the very original image with Pascal's face, ooh, where is Pascal? There he is. Right. So if you think about like the Chan-Vessey results here, where we have the binary segmentation, if we're doing MBO here, then the heat equation step is going to blur the boundary between the different parts of Pascal. But the same thing happens on the graph. So on the graph, you have, it's all discrete points, but you're in it's a lot of them, right? So some points are colored one color and some points are colored another color. And we're trying to figure out where the boundary of the two colors should be. And so how we do that is we kind of bleed the colors, right? So instead of having all the points of one color and another one, you sort of, and you use the structure of the graph Laplacian to do that bleeding.
Okay. Yeah.
Right. So the graph Laplacian is coding information about the it's about the connectivity of the graph, but it's not literally just where it's connected, it's how connected is it. That's the weight functions. That's why we're using a weight. So this is actually, so now this brings up another issue with, with the use of these models for networks, because networks typically are not weighted graphs. The weights are either 0 or 1. You either have an edge or you do not, right? But what's beautiful is that the modularity functional was designed for, just in terms of a functional, it's designed for general weights. So you can take that and just plug and play a weighted similarity graph into, that connection really has not been well explored. You have one body of literature in physics and statistical physics looking at networks, and another body of literature in machine learning and computer science looking at similarity graphs for big data. But there's this lovely connection that I think really needs to be explored more, and we've had a lot of fun doing that. And one of the benefits is you get this unsupervised, you get this way of solving unsupervised problems with unknown numbers of classes. And, that's kind of a gold medal problem in image processing, right? I mean, it's really not easy to do. And I think there's a need for it. And I think it's something that we really should, it's a button that we should be pushing more, in my opinion, as researchers.
Interesting. Yeah, I agree. It's a really exciting direction, kind of different from the sort of common approach for segmentation or clustering.
Right. I'm trying to make that point. And we've had a bunch of people who've been in my group or have some connection to it, have been taking these MBO methods on graphs and trying them on lots of problems. And so far, they're really holding up. I had a student of one of my former postdocs write to me saying, yeah, we came up with this great new method and we're so excited about it, but we ran it against MBO and it's still beating it. I said, yeah, it works pretty well, doesn't it? But one caveat is it finds local minima, right? So if you want to find a global minimum, you have to use a different method. We do have a paper on that, right? So I didn't put it in my slides, but there's a paper we published a few years ago. Katerina was the lead author on that. And we looked at the binary problem and how to find global minimizers, because that's been done already in Euclidean space. So it was a natural problem for us to work on, right? So it turns out that the ideas from Euclidean space, again, carry over very nicely. And there is a relaxation using total variation. There is a relaxation of this binary segmentation problem. There is a relaxation that you can prove like almost always gives you the global minimizer. And so it gives you very nice algorithms, but they're more expensive, right? You can use ADMM for TV without the binary segmentation. You can use ADMM and then do the binarization after the fact, but it's much more expensive to do that. It's like an order of magnitude more expensive computationally to do that. And you may not want the global, there are lots of applications, strangely enough, right? There are applications where the global minimizer may not be the one you want if you're in a very non-convex space and there are multiple local minimizers.
Yeah.
Yep.
Nice. So, any other questions? I guess.
That was a good one. Zach's question was great. I love that question.
Oh, another one from Zach.
Okay, good.
Another one.
You mentioned there's no analog of the Fourier transform. Yes, to projections on the spectrum of the glass, making pseudospectrals slow when many modes are required. Right. The FFT takes advantage of redundancy of the projection of the continuous Laplacian. That's absolutely correct. Do you know any obvious reasons why such redundancies don't exist for the graph Laplacian spectrum in general? So here's the deal, Zach. The graph Laplacian, so I'm assuming my graph is coming from a similarity graph that's generated by actual data, okay? And that's different from taking the graph that we would use in PDEs to approximate the continuous Laplace operator. So in PDEs, if we're going to solve a PDE that has a Laplace operator in it, the simple thing we might do is use finite difference approximations, right? You get, like in 2D, you get a 5-point stencil. So the graph would be, for finite differences, the graph would just be, like the 4 regular graph in 2D, right? It's a graph paper, right? So in that case, your graph Laplacian versus the, your numerical analysis 4-point stencil approximation of the continuous operator, those are the same problem. They're the same problem, right? But for machine learning applications, that's not our graph at all. It doesn't look like the 4 regular graph at all, right? It's a similarity graph that already sort of has natural clusters built into it from how you're constructing the graph from the data. And that's what we're trying to find those clusters, right? So it's a very different problem. And so, because of that, there's a lot of redundancy. If one looks at the modes of the graph Laplacian, so we've done this many times with modes where we can visualize them easily. So the image processing applications are great for that. So you take an image that has some obvious noise just based on how it was collected, and you start, looking at false color images of the eigenfunctions of your graph Laplacian. And what you discover is, and you can order them according to the eigenvalue, right? So you can just so you take the smallest eigenvalue and then the next one and the next one. And those ones starting with the smallest eigenvalue, just like in your standard heat equation, those are the modes that correspond to large scale features, right? And so you'll see the large scale features in the image just popping out of the eigenfunctions, right? So that's what you see. But as you go to higher and higher values of the eigenvalue, the images that you get, like the false color images of your eigenvectors, they just get noisier and noisier. You basically go from features to noise as you scroll through your space of eigenvectors. So what we discover in practice is that at some point you're basically in the noise, and you don't have to go very far with data like our plume data, where there's, where we're looking for basically, 3 or 4 or 5 features at most in this data set that, the one that we did with 7 frames of the video, 280,000 pixels. And we're only looking for a small number of features in the image. So we were able to do a really good segmentation of that data set with, less than 100 eigenvectors out of 280,000 nodes, 100 eigenvectors, right? So it's vastly different from what happens in Euclidean space, right? If we were trying to use a regular image, like if we were trying to do, let's say we were trying to solve that problem like in Euclidean space, right, using the Chan-Bessé algorithm from 2001, and we were going to use the regular, spatial Laplace operator instead, we would be resolving that thing down to the level of the grid, right, of the pixels in the image. We would have to use, the full refinement. Otherwise, we'd get all sorts of spurious effects, right? Right, Gibbs, you get a Gibbs phenomenon, you get all sorts of junk that you just wouldn't want. But because the Laplace operator is created from the data itself, we get we get a lot of the large scale features very precisely, you know, in terms of the spatial embedding. We get them very precisely without having to over-resolve the graph Laplacian. So that's a beautiful thing about that particular mathematical object. Really good questions. The continuous translational symmetry of the continuous Laplacian makes the Fourier transform special. Yes, yes, we're right, because it's a spatial operator. So these graph operators, right? I mean, you can, right there, it's an abstract space, right? The graph is an abstract space. So these issues like translational symmetry just don't have a natural analog in the graphical setting. So that's a really good question. But what's neat is that there still are a lot of things that we've developed over decades, right, for solving PDEs. There's a lot of stuff that we're porting over to this graphical space. And I think it's for me, it's been a great area of research. I think in part because the computer scientists are not experts in PDEs, so they don't know all the tricks that we know. I mean, they know other tricks, right? And we're borrowing their tricks. Trust me, they have their own tricks, right? Well, you know, like this Nystrom thing, right? So we're learning their tricks and figuring out how to bring our tricks to the table. You can tell my background's in PDE, it is, right? Okay, great. Those were great questions. Joe, you're on mute. You gotta unmute yourself. Yeah.
All right. I guess if there are no more questions, thanks for the talk and thanks for all the great ideas. Lots of food for thought, new ideas to try, and in this new sort of field, and also having a background in fluids, I think.
Yeah.
Yeah,
we've been having fun on the boundary between numerical PD and machine learning. Lots of fun.
Yeah, that's a great area of research.
Oh, Kevin's here. Hi to Kevin Dixie. I haven't seen Kevin in years.
Hi, Andrea.
Hey, nice to see you. That's right. So you're in Washington State, so of course you're on this seminar. Yep. Kevin was one of the folks many years ago who helped get me interested in image processing, and I appreciate that very much.
Nice.
Yep.
All right. Great. It was a great talk. Thank you very much, and hope to see you next time in person.
Yeah, definitely. I'd love to come in person sometime. And thank you all for coming. It was a great audience today. Thank you.
Thank you. Have a great weekend.
Yep.